Okay, where we left off was the whole force acting on a charged particle moving at some velocity through a magnetic field. So a couple things about this angly thing on here. So far, this is a Q times V, but the V cross B. So we're looking at the V versus the B is the important thing on the size of this force. So, for example, the greatest angle you would have between the B and the V would be 90 degrees. Well, sine of 90 is 1. That's when you have the greatest force on it. Anything smaller than 90 or between 90 and 180, which means this velocity goes back this way, the smaller the force. Because you can imagine if there's no angle between the V and the B, if they're in the same direction. So if that particle is traveling along the field, there actually is no magnetic force on it whatsoever. Because the sine of 0 would be 0, there would be no magnetic force. If this is a 1 degree angle between the V right here and the B, that's a very small force acting on it. And similarly, if you went back to 91 degrees, this would make this smaller than 1. It's the opposite direction, but it would still be a force, but it'd be a smaller force. So to have the very largest possible force on a charged particle, you'd shoot the thing perpendicular to the magnetic field. Because if it moves along the magnetic field or backwards, because if you put a sine of 180 in there, meaning it's 180 degrees, that's also a 0. There's no magnetic force on it whatsoever. So the angle is only between the velocity and the magnetic field. That's where the cross product is. And this shows you the magnitude of the force at a right angle to that. So it's still going to be at a right angle to this, but this angle is between the V and the B. All right, let's do some examples of this stuff. Oh, so here talking about the thumb points in the direction of the velocity, fingers point in the direction of the field. The palm is the pointer of the force. There's a lot of right-hand rules. Some even put the right-hand rule that if the thumb points up for the direction of the velocity, the hand points to the magnetic field, sometimes they'll point a finger in for the direction of the force. It's a lot easier just to use the palm for the direction. Think of the force that you're pushing on something with the palm. And if it's an opposite charge, you use your left hand, or it's the opposite force. Okay? So everything's opposite for negative charge. Alrighty. So, quick question for you then. So let's say if you have a charge moving, now this is a positive charge moving out of the page. So it's not this picture. For some reason they threw that picture in here. So the velocity is actually towards your face right now. But the field still goes to the right. Oops, that's actually the opposite of this direction. So it's not this picture whatsoever. What direction is the force? So you take your hand, you go velocity is out of the page. That's towards my face. That's where my thumb's pointed, towards my face. But since the field is to the right, like so, that means there's an upward force pushing on this positively charged particle. So let's say it's still going out of the page. It's still towards my face. That's right out of the screen. But the field is to the left. So that's this way. Well, that means the thumb points right at my face, out of the page, but the force is now down on the thing. So I think here's your question coming up. So it's still coming out of the page, but the field is up. What direction is the force acting on the thing? Think about it. Pause if you need to. And then pause. So if it's coming out of the page, the field is up. Well, what direction is the force? Well, it's this way. So the palm of the hand, which is to your left. Okay. What if it's out of the page and the field is down? Well, it's coming out of the page. Thumb still points towards your face, coming out of the page there. But the field is down, so what direction is the force? It's just the opposites to the right. Okay? So that's how you use your right-hand rule. Now we're getting a little more complicated. We're shooting a charged particle into a realm where there's a magnetic field, and it gets bent and goes into another realm of a magnetic field. At least we believe it to be magnetic. There's got to be something there to cause that to curve. So each chamber has a unique magnetic field. A positively charged particle, so using the right-hand rule, because it's positive, it's negative, use your left hand. Enters chamber 1 at 75 meters per second, straight up, and follows a dashed trajectory. What direction is the force on the particle just as it hits that region of the magnetic field? Dum, 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 dum. Don't have time for that. We need to do pause. So thumb points upward, and I can see the direction of the force, the direction of the force is to the right. Since it's going upward and the direction of the force has to be to the right, I got to flip my body clear around like this. Because the force is going up, but it's to the right. So what direction is your hand pointed? Because that would be the direction of the magnetic field. Oh, what direction is the force on the particle? My bad. The force is to the right. So that's why it's turning. Remember, you need an unbalanced force to change directions. So the force has to be to the right to make that turn. I'm already on the second question already. So the particle is moving straight upwards but veers to the right. The next question is going to be what direction is the field? That's when you're going to have to whip out that right-hand rule. Okay, so what direction is the magnetic field? Remember, it's going upwards. The thumb goes up. The force is actually to the right, so we're going to turn around like this. And which way is that magnetic field? Can you say out of the page? So this is the rule for the right-hand rule. It's not going in that direction because remember, the velocity is up, but the force is actually to the right. That's why you got to turn your body around, and it's pointing out of the screen, your hand. That means that's the direction of the magnetic field, is right towards your face. Okay, so there it is. So here's the thing about drawing in 3D. If we're going left or right or up or down, you can show an arrow, but I can't really show an arrow if it's coming right for me. So what we usually do to represent a magnetic field coming out of the thing, look at it like a missile. That's like that point on the missile, and it's coming right for you. So if it was going into the page, this would be a big fat X, like if it's an arrow. If you shoot an arrow and that arrow goes away from you, you're going to see the back feathers on that. So if you see an X like this, that means the field is actually into the page anytime you see X's. But if you see a circle with a dot in the middle, that's that's the arrow coming right for your face right there's coming out of the page. So that's how you do directions in 3 dimensions, because you can't show it coming towards you away from you. X is moving into the page, the dot is coming right at you. All right. So what's the direction? How about region 2? Same story, you've got your thing going to the right, so make your thumb go into the right. And the force is upward on the thing. So if the force is upward on the thing, that must mean the magnetic field is which way? Which way? Which way? It's going to be into the page. Okay? So it's going to the right. The force is upward. That means that field is actually along my fingers going into the page. Okay? All right. So you notice there's an X. That's like an arrow going away from you. Look at the feathers, or the back part of the bomb is, or missiles going away from you, is the little fins on that thing going away. However you want to think about that. Alrighty, so the force depends on the magnitude of the charge, the magnitude of the velocity, and the magnetic field. Well, not just the magnitude of the velocity, it also depends on the direction of the velocity compared to the magnetic field. Because as this approaches 0, there is no force. But the maximum force is at 90, just like we talked about a second ago. So for maximum force, you want those perpendicular, okay, for the maximum amount. So as long as the velocity is, but the point is, to find the force, we need to know what that angle between the velocity and the field is what you have to know for sure. Okay, so it's only the component of the perpendicular component to each other really counts. Okay, in either one of those. So if it's parallel, there's no force whatsoever. Okay, so it doesn't matter if you use 0 or 180. Alrighty, so here we got some, we got a quiz question coming up here. 3 charges have equal charge and speed. Oh, so Q times V is going to be the same. So now we're wondering about the magnetic field, but they're traveling in different directions in a uniform magnetic field. So they all have the same magnetic field. Well, that's sweet. Which particle has the greatest magnetic force? Well, it's the one with since they're all the same charge and speed, it's the one that's closest to 90 between the direction of the field and the direction of the velocity. So that would be number 2. So number 2 is the greatest angle. That means it's going to experience the greater force. Okay, don't worry, there's more questions. Next question. So force on particle 3 is in the same direction as on particle 1. True or false? Well, let's look at number 3. So number 3, the field is indeed this way. But the velocity, I can't bend my thumb back, but if I could, it'd bend back in this direction. That means the force is still inward. Not a big force because it's a very small angle, but a teeny little force inward. Let's do the number one. Number one, the field is this way as well. And once again, the velocity is at a small angle, but it's still got a little bit perpendicular, so the force is actually still into the page. So it turns out that's a true statement. 3 and 1 are in the same direction. In fact, 2 has a same force in the same direction, but it's just a greater force because it's moving the same speed, but it's closer to perpendicular, have a greater force at that moment into the page anyway. So that is a true statement on this bottom one. Okay, they're both in the same direction. All right, comparison of the two, electric versus magnetic. So to have electric forces, you have to have charges. Okay, well, to have a magnetic field, you have to have moving charges for the source. Okay, so the charges act on each other. These charges act on other moving charges. So every time you have a moving charge, you actually have a magnetic field. So you have to have a couple moving charges or a source that moves charges, whether it's a bar magnet or a coil of wire that's moving charges, that makes a magnetic field so they can push on each other. The magnitude depends on, for the field, how big the charge is in that field. For this, it depends on what the charge is, just like here, but how fast it's moving is the key thing, because you have to have a moving charge. Not just how fast, but in what direction is it compared to the magnetic field. Because if they move in the same or opposite direction of the magnetic field, there is no force. And finally, direction, it's parallel to the field, depending on if you're positive or negative, it's one way or the other directions. But this force is actually perpendicular, okay? It's a perpendicular force to the velocity in the magnetic field. It's in the third dimension. Alrighty, so here's what we notice the title velocity selector. What's up with that? Well, you have a electric field that's pointing down. They're telling us that. And the direction of the magnetic field are set up so a charged particle with initial velocity v can travel straight through. How can a charged particle go through a magnetic field and electric field and not go up or down? Well, if the electric field is down and we only have electric field, and this is a positive charge that goes through there, it's going to drop and hit down here. You can't hit the other side. And it's moving really super fast that the hole's big enough it can make it. It can't make it down there. So what direction does the magnetic field have to be to keep that from falling? Well, the magnetic field has to be in the opposite direction to make that happen. So you have to have a magnetic field. So what direction is the magnetic field to make that happen? Well, the force is upward, but now that's the big question. So to keep that going straight through there, the force is downward, following the electric field in the same direction. But the force of the magnetic field has to be opposite of that. It's in the opposite direction. So here's the thing. It doesn't matter how fast it goes through for the electric force, it's the same force. But the faster it goes through here, the bigger the magnetic force. So the key thing is you want to shoot this at just the right speed so you have the same magnetic force up on the thing as downward. Pop quiz, what direction is the magnetic field in this thing? What direction is the magnetic field? Charge is going in. Charge is going in, and the force is up. That means the magnetic field is actually into the page. So even though the electric field is straight down on the screen, the magnetic field is indeed into the page. That's why there's an upward force. But this is called a velocity selector because we could change your magnetic or your electric field and make it go higher or lower depending on whatever we need to go through. Because if the particle is going too fast, that means the magnetic field is larger. It's going to go up and hit up here. If the particle is going too slow, now the electric field, which doesn't change, is bigger than that. It's going to go too low and it's going to miss. So by having the right combo between the magnetic field and the electric field, you can actually select what speed of particle you want to keep on going and get rid of everything else. So electric force is down, magnetic force has to be up. That must mean by the right-hand rule, B is into the page. Okay? So that means the electric field is the same as the magnetic field. So Q times E is the same as Q times V times B. We don't need to know the size of the Q actually. So it solves out that the velocity is your E over your B. So you can change your electric field to get a faster or slower moving particle if you need a certain